Okay, we said that torque was equal to a force times distance. Now, the only thing about this distance is it must be perpendicular. So I'm going to put a little symbol over here showing that this is perpendicular to a surface. Okay, now oftentimes you will have a force that isn't perpendicular to the surface, but we'll cover that in a second. So first let's create a picture. Let's make this picture a, here is a wrench, and that wrench is attempting to tighten a bolt. I'll put the bolt right there. We're going to add a force to this. That force is going to be straight up. Okay, so that it forms a 90-degree angle right here. Now, this is the force. This is the target that we're trying to twist. That's our pivot point. So let's just call that the pivot point. So the force is going to be pivoting around this nut right here, and the thing is going to try and turn. So how much torque is applied to this? Well, torque is going to equal the force times the distance. Here is the distance. I told you some books call it D and some books call it R. We're going to use a simple D for distance here. So if this force was equal to 10 newtons, and the distance was, let's make it easy, we'll make it 1 meter. It's a very big wrench. Then our torque would be equal to our force times distance, which is equal to, it's already perpendicular, 10 newtons times 10, 1 meter, 1.0 meters, which would make our torque 10 Newton meters. Hopefully that's pretty obvious. The only difference occurs if the force, let's erase everything we did. Actually, we'll keep it there and we'll just draw another one. Here's our wrench. And there's the nut we're trying to turn again, right over there. But let's say we came in at an angle of force like this. There's our force coming in. Okay? Now I'm exaggerating, but this is our force coming in. Here's what you have to do. Here's our distance of the wrench. We'll keep it at 1 meter. Okay, we'll keep our force at 10 newtons. But we'll set this up to an angle of 45 degrees. This is what you must do. You pick the pivot angle point, and you must draw a line from the pivot point such that it intercepts the force line at 90 degrees. So this is 90 degrees. Now our formula changes just a little bit. Now our formula becomes torque is equal to force times the distance times the sine of that angle. Now our force is still 10. Our distance, we said, is 1 meter. But we have an angle. So we're going to have to include in this formula the sine of 45 degrees. You can see now this is going to be our new distance. We'll call it distance prime if you'd like. Just show it's a little bit different. Our force is still being applied. It's actually being applied to this spot, but the effect is though we're applied to a distance that is much shorter now. So the solution becomes 10 newtons times 1, and the sine of 45 is 0.707. End result is our new torque is 7.07 Newton meters. Okay, so sorry about the echo in the last recording. I think that's been fixed now. So again, the idea with torque is that there must be a distance somewhere that is perpendicular to the force applied. Well, here's the force applied again. Okay, it was 10 newtons. 10 newtons there. But the distance was 1 meter and it wasn't at right angles. So in order to create right angles, we had to use the full torque formula. Again, the full torque formula is torque is equal to force times distance times the sine of the angle. Okay, now that we've done that and we know what torque is, let's do one more just in case you're confused and it seems as though you can't draw a right angle. You can always draw a right angle. There can always be a right angle. I'll show you what I mean. Let me move this down a little bit. And let's show you the same picture again. I'm going to draw the wrench just as we had before. Okay, this time it's going to be a red wrench, I guess. Okay, there's our target. Now I'm going to show you that force coming in like this. This is still a force equal to a force equal to 10 newtons. And I'm going to keep this at 45 degrees again. Actually, I'm going to yeah, let's keep this at 45 degrees right here. Undo that, not 45 degrees right there. I'm going to keep that at 45 degrees. That 45 degrees is going to be right here. Okay, so what do you do now? It's obvious that you can't draw coming up this way and get a right angle. So all you do is extend the force as though it were going through the object, coming down like this. And you draw you pick your pivot point, still right there, and you come down and intercept it down here. There's your 90 degrees again. If the 45 was on this side over here, then hopefully you had a little trigger and you can realize that 45 ends up being on this side. The end result is the same formula we had above. Okay, torque is equal to force times distance times the sine of the angle. Except this is just a little bit different from what you had before. Now always keep in mind that you're looking for a triangle. You're creating a right triangle. That's really what you're doing here. So when I pull this out, if I can, that's my right triangle. And here is the 90 degrees right here. Pardon my drawing. It's a little hard to draw with this pen. I'm not used to it, but there's your 90. There's your 45. This is your opposite side. And this is going to become your new distance, your distance prime, just like it was up here. Okay? So those are the two rules when you're coming in at an angle. Look at them. Make sure you draw a line from your pivot point to intersect the force at right angles, even if you have to extend that force downward like so. Okay. Torques involve a force and a distance all the time. So here's a problem we've done in class several times. I think we've done it 4 times, but in preparation for the test, in case anybody was absent or in case you forgot how we did it, I'm going to go through it again. First, let's read the problem. It says, 2 people are holding up the ends of a 4.2 kilogram wooden board. Okay. Okay, so that's this board right here, and we're going to refer to it as a table so there's no confusion. That's a table, and it's being held up by the ends, right on the ends, right there. So I've kind of shown that right here. Here are the 2 forces holding it up. We'll call this a force, and we'll put a suffix on it in a second. And this is a force. That's what's holding it up. Okay, 2 forces holding it up. Now it says that the whole board is 1.75 meters long. So from this point all the way to this point is 1.75 meters long. Okay, it says a 6, now I'm going to write this down by the way. The mass of what I'm going to call the table, so as not to confuse it, is equal to 4.25 kilograms. Now, since we're talking forces, we know that mass is not weight, and a force is weight. So I've got to convert this to a force if I want to know the weight. I'll put it right over here. Force weight is equal to whatever the mass of the table is times gravity, which is equal to 4.25 kilograms times minus 10 meters per second squared, which gives us 42.5 newtons for the table. I'll make sure we know that's the table. This is all my stuff that I know. It goes on to say that besides being 1.7 meters long, that there's a 6, and I'll put this 42.5 over here now that I solved that, 45 newtons. And you can see we're going to do the same thing with the 6 kilograms. That is, kilograms are not weight. Let me read the whole thing first. A 6 kilogram box sits on the board 0.5 meters from the end. Well, let's put that 0.5 meters right here while I'm there. This is 0.5 meters to the end, right to here. Okay, and I'm going to convert this, same as before. Force weight is equal, that's the force weight of the box, is equal to the mass of the box times gravity, which is 6 kilograms times minus 10 meters per second squared, which gives us the 60 right here. That gives us the 60. Force weight of the box is equal to 60 kilograms. Now I can put those right over here. They're going to be useful. So the force weight of the table is equal to 42.5 newtons, and the force weight of the box is equal to 60 newtons. And I can put that right in now. 0.5 away is where the box is, and I have 60 newtons right here. Since it's going down toward the ground, and since these are both negative, negative 10, Okay, I've got that force pulling down. But where do I put the 42 newtons for the table itself? The rule says that if the table is nice and uniform, it's not thicker on one end than the other, then that weight shows up right in the center of the table, right there in the center. The box is here, okay, at 0.5. And the table's weight is going to show up right here, halfway down the full length. So let's show that. Halfway down the full length, I'm going to say that's about here. I'll make it a little longer just so we can see. It's just so I can draw the dimensions. Okay, so let's see what that does for us now. We know it's 60 newtons. I mean 42.5 newtons, so let's make sure we put that in there so we don't forget. This is a minus 42.5 newtons. These two are pulling down. The guys are holding it up. Let's put some, we'll call this force 1. We'll call this force 2. We'll call this force 3. And we'll call this one over here force 4. So now we have numbers, we know what they are. Now let's put that last thing we know, that the distance of the table from the end is 1.75 divided by 2 meters. Now, so far this should all be nothing more than a review. We've done this several times now. And let's just make this a little simpler. We're going to make this 87.5. 175 divided by 2 is 87.5. Okay, the only reason I showed it as a fraction over here so you can see where it came from. It's half the distance of the whole table. All right, so we have all our information. Let's make sure we have it. Here's one force pulling up, so it's going to be positive. Another force pulling up, it's positive, and we got two negatives pulling down. Here is all you do. We are trying to solve for how much force the two people have to exert. So we have two things we don't know. We know all the weights pulling down, but we don't know what the forces are pulling up. And we have two unknowns, so we are trying to find over here F1 and F2. We can't solve two unknowns, but luckily we're going to solve this using torques. Now, a torque is a twisting. We know that. It's a twisting around a point. What we have to do is pick a point. Now, we can either pick this point right here because, and I'll show you why in a second, or we can pick this point. Let me explain to you why we're picking this point. I'll do it in red. If I pick this point right here, okay, then the torque created by F1 is equal to F1 times distance 1. But there is no distance. This force is applied directly to that point, which means this is 0. Okay? Now that we know that one, let's go to the next one. Okay, this guy's going to be trying to twist it. I'll mark him in, let's mark him in yellow. This guy right here. Oh, that's a lousy color. We can't see that, so we'll do it in green. This guy right here is trying to twist this in this direction. This will be, if we're calling this force 2, let's call this torque 2. And if this is F3, you can see he's trying to twist him in the same direction. And we'll call him torque 3. And finally, the only guy that's stopping this from turning, since F1's out of the picture, is F4. And we'll mark him in blue. F4 is the only guy torque 4 that's trying not to turn him. So let's see what we have for these values now. Torque 2, might as well keep them in green, right? Torque 2, our green guy, is going to be equal to force 2 times distance 2, which is the same as, well, what's our force? Well, there's our torque 2. It's a minus 42.5 newtons times, what's the distance? Oh, it's 87.5. I'm sorry, 0.875. Ooh, don't let me get away with that. That should have been 0.875. Let me just back up and fix that. Always good to check your work. This guy is 0.875 because the whole distance is only 1.75. So 0.875. Now let me get my calculator going here and multiply that out. We'll see what we got. We got 42.5 negative times 0.875. And that gives us an answer of 37.2 rounded up. So this is going to be equal to, this is meters by the way, it's going to be equal to 37.2 Newton meters. Newton meters is torque. Well, what do you know? That's an important answer. We got that one right here. I'll circle it. It's going to be important to us. Now, let's do the next one. Torque 3, also green, is going to be equal to force 3 times distance 3, which is equal to, here's our force 3, a minus 60 times, what's the distance? Well, if he's 0.5 meters from this end, okay, this is the point. Here's the arm that we're twisting around. Remember, force is equal to torque times the distance. Well, here's our distance all the way over to here, and there's our force. It's at right angles. You can see it's right angles right here. So that's good. But if the whole thing is 1.75, then this distance right here, okay, I don't want to confuse it, but at this point, going from here all the way back to this guy right here is going to be 1.75 minus 0.5, or 1.25 meters. So I can put that in, 1.25 meters. My calculator says minus 60 times 1.25, clear, minus 60 times 1.25 gives me 75.6 as an answer. 75.6 Newton meters. And again, this is another important value that we want to remember. Finally, we got one more left. We'll do it in blue. Torque 4 is equal to F4 times distance 4, which is equal to a plus, I don't know the values, I'm just going to put in F4, times 1.75. And that's all I can do on that. I've got 3 important values. Actually, I've got 4, because this is important to us too. Now, is this table twisting if they're lifting it straight up? No. So all the torques must be canceling because it's not twisting. So, remember the symbol? It means sum. Sum of all the torques are equal to 0. That means torque 1 plus torque 2 plus torque 3 plus torque 4 must all equal 0. All right, torque 1 from up here. Well, that is 0. Plus torque 2. Well, plus torque 2 is going to be plus a, it should have been minus, it should have been minus 2, plus a minus, always good to go back and check your work as you're going along. We know they have to cancel, and if we don't put them in right, they're not going to cancel. Minus 37.2 Newton meters. And I always like to put little dots showing where it came from. Plus, and that's going to be this one, plus a minus 75.6 Newton meters. Plus F4 times 1.75 meters. And all this has got to equal 0. Well, I can add these two together right here, and that's what I'm going to do. I'm going to show dots here showing that I'm adding these two together. I'm adding those two together, which means we have minus 37.2 minus 75.6. Oh, calculator didn't like that. Let me do it again. 37.2 minus 75.6. So I'm two negative numbers. It's going to give me a total of minus 112.8 Newton meters plus F4 times 1.75 meters. That's that guy. All equal to 0. I'm going to move this guy to the side of the equation. That makes this F4. Anytime I change the other side of the equation, the sign changes. So this becomes 112.8 Newton meters. But I don't want Newton meters, and I don't want this to be 1.75. So I'm going to divide this by 1.75 meters, and I'm going to divide this by 1.75 meters. Well, I already know meters and meters cancel, leaving me just newtons. That's good because it is a force. So the force of F4, the force that guy is lifting up with, is 64.5 newtons. So I now know that this guy is lifting up at 64.75 newtons. But I also know this table isn't floating up this board and it isn't going down, which means all the forces must be in equilibrium. They all must be equaling 0. That's the hint right there. So I can write that down. Right down here, my next part. Sum of all the forces must equal 0. That means F1 plus F2 plus F3 plus F4 must all equal 0. Well, F4 is no longer 0 now because I'm not talking torques. So F1, rather, is going to stay as it is. But I do know what F2 is now. F2 was right over here, minus 42.5. And F3 is going to be minus 60. So it's going to be minus 42.5 newtons. That's this guy, plus a minus 60 newtons. That's him. And plus, I now know that pulling up in the other directions is this guy right here, 64.5 newtons. Let me just check my signs here. I got 2 going down toward the center of the Earth. That's because gravity's pulling them down, and 1 pulling it up. So I'm going to combine all these. This is going to give me a bigger number, a big negative number, adding to this. So adding them all, I've got minus 42.5 minus 60, and my calculator is giving me something with 10 digits, so I got to start again. So after I add all these up, I find out, move it to the other side of the equation, I find out that the force that's left is 38 newtons. And that's my final answer. So let's go up and see if that makes sense. I've got 38 newtons pulling up. I've got all my answers solved. I've got F1 and F4, which is what I was looking for right over here. F1 and F4. I've got them solved. Let's see if it makes sense. Okay, if this wasn't here, if the minus 60 wasn't here, could you see that both these guys would be lifting equally since the weight's right in the center? But it's not. We got another box over here, which makes this guy end up carrying more. It's more toward his side than it is this. And the 38 plus the 64.75 equals what's going down. So that's my final answer. And I know it's correct by just taking a quick look at it and doing the sum of the forces. And that's how you do it. Now, it looks complex, but go back and listen to this again. I did it step by step. First finding out what all the individual torques were. Well, first, identifying what I have and drawing a picture. This is 1. This is 2. I drew the picture. 3. I found the torques, including the sum of the torque. I can count this as 3 also. And finally, the last step was a sum of all the forces. Go through it. Stop it if you have to. Shut it off. See if you get the same answer.